Good day, and welcome back to the Deep Dive. This week, 3i Atlas reaches a geometry we've never seen before, and quite frankly, one that we might not see again for another generation of interstellar surveys. If you've been tracking the orbital parameters since perihelion, you know we've been waiting for the calendar to hit January 22nd, 2026. That is the date, just 8 days from now, when the phase angle of this object collapses to an almost impossible 0.69 degrees. We are talking about a near-perfect alignment between the Sun, the Earth, and the comet itself. This isn't just another data point in the ephemeris. This is the zero-phase alignment we have been theorizing about since detection. As of today, January 14th, we are watching the angle narrow hour by hour. Most comets native to our solar system are rarely observed at phase angles below 10 degrees due to orbital mechanics and safety limits for ground-based telescopes pointing near the Sun. Even our last interstellar visitor, 2I Borisov, frustrated astronomers by never dipping below 16 degrees during its observable period. It kept its secrets hidden in the shadows of its own surface roughness, but 3i Atlas is breaking that rule. Let's look closer at the data coming in from the high-precision photometry teams. We are looking at a window that opens on January 19th and stays open until January 26th. That is an entire week where the phase angle remains below 2 degrees. This is the surge window, and right in the middle, on the 22nd, we hit that 0.69 degree minimum. This is opposition surge territory, a region of optical physics where the rules of brightness change dramatically. Why does this specific angle matter? Because when you look at an object with the Sun directly behind your head, shadows disappear. Literally every pebble, every dust grain, every fractal aggregate on the surface or in the coma hides its own shadow from your view. The result isn't just a linear increase in brightness, it's a spike, a nonlinear dramatic surge in intensity that tells us things about the surface texture that no spectrum or standard image ever could. At the moment of this peak alignment, 3i Atlas will be roughly 3.33 astronomical units from the Sun and 2.35 astronomical units from Earth. We are projecting an apparent magnitude of V approximately 16.7. That is faint for the naked eye, but it is like a beacon for 8-meter class telescopes and optimized smaller apertures. They are all swinging into position right now. The schedules at Cerro Paranal and Mauna Kea have been wiped clean for this. If you're relying on standard public feeds, you're missing the granular breakdown. Hit that subscribe button now to make sure you get our nightly analysis. The geometry here is critical. Ordinary comets don't give us this look. They stay sidelit or backlit relative to us. To get a front-lit view, what astronomers call opposition usually requires a planet with an orbit outside Earth's, like Mars or Jupiter. But 3i Atlas, with its hyperbolic, high-inclination trajectory, is cutting through the plane in a way that lines it up perfectly with our sightline to the Sun. This is why the mood in the community is so tense. We aren't just taking pictures, we are waiting for a specific physical phenomenon to trigger. If the brightness spikes exactly as the angle hits 0.69 degrees, it confirms we are seeing the opposition surge. If it doesn't, or if the curve is flatter than predicted, we have to rewrite our models of what this thing is made of. This is our first true shot at understanding the microtexture of interstellar material. We have models for zodiacal dust and Kuiper belt material, but zero observational data for the phase curve of an interstellar object at sub-2 degree angles until next week. It means instrument calibration is happening now. Polarimetry, measuring the polarization of the light, is going to be just as crucial as the brightness. As the phase angle drops, polarization usually goes to zero or flips, telling us if the grains are singular or fluffy aggregates. As we established, the window opens on January 19th. To understand why we are holding our breath, we need to look at the raw physics of light. We are entering a domain dominated by two different mechanisms. The opposition surge isn't a single phenomenon, it is a composite effect. First, we have shadow hiding. Imagine a forest seen from an airplane. When the sun is directly behind you, you don't see the shadows of the trees because the trees cover them. This effect dominates above 2 degrees and tells us about macroscopic roughness. But below 2 degrees, something much stranger takes over. Coherent backscattering. This is where the wave nature of light interferes with itself. When a photon enters a dust cloud and bounces around, if the entry and exit paths are identical, which happens when the sun and earth are perfectly aligned, the light waves interfere constructively. They amplify each other, creating a narrow, intense cone of light directed straight back at the source. This is the brightness spike we are hunting for. This is getting deep into photonics, so if you have questions about scattering versus reflection, drop them in the comments below. Why is this distinction vital? Because coherent backscattering only happens if the size of the dust grains effectively matches the wavelength of light. It is a direct probe of the microscopic structure. If we see a sharp spike on January 22nd, it proves the dust is a complex medium of scattering particles. The amplitude and width of the spike map directly to physical properties like the mean free path of the photon. These aren't just buzzwords, they are the genetic code of the comet's coma. We are effectively using the sun as a laser probe, and because Earth is sliding into that 0.69 degree slot, we are the detector catching the interference pattern. If we see a completely flat line, it would imply a material so dark and absorbent that constructive interference is killed off. This connects to the albedo question: is 3I Atlas dark like coal or bright like fresh snow? The shape of the curve next week decides the winner. The amplitude of the spike will settle the biggest argument in planetary science. In our solar system, comets are remarkably dark. Rosetta's Comet 67P had an albedo of about 0.06, darker than fresh asphalt. If 3I Atlas shows a high-amplitude spike, it would tell us it's shedding pristine icy material that hasn't been darkened by billions of years of cosmic radiation. This phase curve can also reveal the fluffiness of the particles, what we call fractal aggregates. Imagine a dust bunny versus a solid pebble. A fluffy aggregate allows light to penetrate deep and bounce around, enhancing the surge. A sharp, narrow spike points to porous aggregates that formed delicately in a low-gravity environment. We are trying to decode the history of a star system light years away by looking at how a dust grain reflects sunlight here today. We can't fly a sample return mission. The opposition surge is our sample return. We are touching the dust with photons. Building on this alignment, let's flip the perspective for a moment. Imagine you are standing on 3I Atlas on January 22, 2026. You look back towards the sun and you see the Earth. Because the phase angle is 0.69 degrees from our perspective, the reverse is true for the comet. From that vantage point, the Earth will almost transit the face of the sun. This geometry turns the Earth into an exoplanet transit target, and 3I Atlas is the observing platform. We spend billions on telescopes to watch distant stars for planets. Right now, 3I Atlas is in the perfect seat to perform transmission spectroscopy on us. If there were spectral instruments on that comet, they would be detecting solar photons skimming through Earth's atmosphere. They would see the spectral fingerprint of a habitable, inhabited world, oxygen, ozone, and methane, but they would also see technosignatures, industrial pollutants and complex molecules that nature does not produce. If an alien observer were sitting on 3I Atlas scanning the spectrum, the detection of CFCs would be the smoking gun of a technological civilization. The trajectory of 3I Atlas makes this possible. It is retrograde and inclined only slightly to the ecliptic, holding it in the transit zone longer than a typical comet. This mirroring effect, us studying the comet while the geometry allows it to study us, highlights the reciprocity of this alignment. We are validating our own search methods for exoplanets. If we couldn't detect Earth's biomarkers from the position of 3I Atlas, we have no hope of detecting them 100 light-years away. It is a benchmark test using Earth as the subject. 3I Atlas is doing double duty. It is a mystery to be solved and a mirror reflecting our own biological signature back into the void. We are about to stare down the barrel of a beam reflected from interstellar space, viewing 3I Atlas not just as a rock, but as the ultimate laboratory.